What I'd like to do here is give a quick walkthrough of the relationship between the truth table definitions for our logical operators and the decomposition rules for their use in generating truth trees. So at the top here, what I have are the truth table definitions for our operators, the definition for and, the definition for and, the definition for or, the definition for the conditional, the definition for the biconditional. And then what I have below are the truth tree decomposition rules for the unnegated version, and then the truth tree decomposition rule for the negated version. And what I'm going to do is talk through the way that what the rule tells us to do is related to what we know about the truth conditions for statements of those form on the basis of our understanding of the truth table definitions of the operators. So if we start with conjunction here, we see that the truth conditions for a conjunctive statement, and here's the one case where the conjunction ends up being true, require both the truth of the left conjunct and the truth of the right conjunct, right? Both our p value and our q value are t in the one case where the value assigned to p and q is t. So what we do when we come down here to look at the decomposition rule for conjunction is we say we're going to make it our we're going to adopt a convention of getting rid of the conjunction sign and stacking the statements on top of each other. Right? So what this says here is, okay, we have decomposed the statement that we started with, P and Q. We've checked it off to say that we have decomposed it, and what we've done is we've stacked the truth conditions for that on top of each other. In order for P and Q to be true, that is for the whole conjunction to be true, P has to be true and Q has to be true, and then we've justified that by reference to our conjunction decomposition rule. So again, whenever there's only one way for the complex proposition to end up being true, we're going to stack. Whenever there's more than one way, we're going to branch. And so when we come down here to the case of the negated conjunction, right here, right, we see that if the value of the conjunction here is false, right, it has to be false in order for the value of the negation outside the parentheses to be true. So these are the cases that we're looking for when we have the negated conjunction. We're looking at these three lines of the truth table where the entire statement ends up being false. And so we notice there that there are two different ways in which the entire statement could be made false. We see that whenever our p-value is f, the whole thing is f. And whenever our q value is f, the whole thing is f. Right? So that what that tells us is we don't know which of those is the case, but we do know that either not p or not q. Right? So this is right here, this branching, we take the branch to indicate two different ways in which the truth conditions for the whole could be satisfied. The truth conditions for that whole negated conjunction are going to be satisfied in the case where not p. They're also going to be satisfied in the case where not q. We don't know which of those, in any particular case, which of those is satisfying the truth conditions, but we know that at least one of those has to be. So what we've done is we've decomposed this complex statement that involves a negation and a conjunction, and we have represented it graphically in such a way that we no longer need to make use of the conjunction, and so we branch either not p or not q and justify that by reference to the negated conjunction decomposition rule. All right, so what we've noticed here, we're going to notice with the others as well. That is, whenever the non-negated version, as it is here, if the non-negated version stacks, there's only one way for it to be true. There's going to be more than one way for it to be false, so the negated version is going to branch. If the non-negated version branches, as we'll see with disjunction, then the negated version is going to stack. So if we focus on disjunction for a moment here, Right? We see that when we look at the truth table definition, that there are 3 lines of the truth table where the disjunction is true. There's only 1 line where it ends up being false. Right? So if we want to graphically represent the truth conditions for P wedge Q, we represent it by branching out from the statement and saying either P is true or Q is true. Right? Because these are the 3 cases that we're looking at. We recognize that whenever, in any case where P is true, the whole thing ends up being true. And in any case where Q is true, the whole thing ends up being true. Right? So the truth conditions for P wedge Q can be represented by branching with P on one side and Q on the other side. Now, since there are 3 different ways for the statement to be true, there's only 1 way for it to be false. And so the negated disjunction is going to stack. So this is the line of the truth table that we're interested in. This line here is the line of the table that we're interested in when we're saying that the negation is true. Right? So, so there's 1 combination of truth values, right, which leads to the P wedge Q being false. Right? So we know that on that line of the truth table, P is false and Q is false. So we stack not P on top of not Q. And then we justify those by reference to negated disjunction decomposition. Check it off to indicate that we're done. And that's all we do there. Right? So with the disjunction, there is only 1 way for it to be false. And so negated disjunction stacks. There are 3 lines of the truth table where the disjunction is true, so the disjunction decomposition is going to branch. Now, when we move over here to the conditional, we have a similar case to disjunction. There's only 1 way for the conditional to be false, and there are 3 different lines of the table where it ends up being true. So the rule for disjunction decomposition is going to branch, right? Because there's this line, and this line, these 3 lines here. Right? So we know either, what do we notice when we look over at the values here? We notice that whenever P is false, the whole thing ends up being true. And whenever Q is true, the whole thing ends up being true. Right, so the truth conditions for the conditional statement can be represented by branching, and on one branch putting not P to correspond to P being false, and on the other branch putting Q to correspond to Q being true. So that's why the conditional decomposition rule tells us to branch and to put the negation of the antecedent on one side and the consequent on the other. Now, because the conditional decomposition rule branches, we know that the negated decomposition rule is going to stack. There's only 1 way for a conditional statement to end up being false. Right? That is the way that is signified here by this F. And then we look over here and we look at the values of P and Q when that occurs, and we see that in order for the negated conditional to be true, right, we have to have a true antecedent, so we stack P on top of a false consequent, so we stack P on top of not Q. We justify each of those by reference to negated conditional decomposition, and we check that off to indicate that we have taken care of that statement. And again, what we've done is we have simply graphically represented the truth conditions for the statement that we started with in a way that doesn't involve the two-place operator that was in the statement that we started with. All right, so our final operator, the biconditional. We notice the uniqueness of the biconditional is that this is the one operator where we have 2 rows of the truth table where it ends up true, and we have 2 rows of the truth table where it ends up false. So what that's going to translate into in terms of our decomposition rules is that when we represent the truth conditions for the biconditional itself, then that's going to branch, as it does here. And then also when we represent the truth conditions for the negated biconditional, that's going to branch as well. So there are two different ways for the biconditional statement to end up being true. And when we look at that, we see that it is true in this case and in this case. Right? And this case is the case where P is true and Q is true. So we stack P on top of Q there. This case is the case where P is false and Q is false. So we stack not P on top of not Q there. Right? If the biconditional is true, we know either that they are both true, as indicated there, or that they're both false, as indicated there. Now when we go to the negation, instead of looking at the two lines of the table where it ends up being true, we look at the two lines where it ends up being false. Right? And then we indicate, okay, this is the case where P is true and Q is false. So one possibility that renders the negated biconditional true is the possibility where we have P and we have not Q. And that's what we represent over here on this branch. The other possibility is the possibility here where P is false and Q is true. So the other possibility we'll write on the other side of the branch is not P on top of Q. Right? So again, what we're doing in all of these cases, what the decomposition rules allow us to do is simply to represent graphically the truth conditions for the statements that we started with in ways that don't contain the operators, the two-place operators that we started with. And so the process is going to continue until all we have on any given branch is a statement letter or a negated statement letter, or all that we have on the branches are statement letters and negated statement letters. And then we can use the notion of statements and their literal negations to tell us whether any of those branches closes. And in the next little segment, we'll talk a little bit more about open branches and closed branches and how those relate to our ability to determine the logical properties of propositions, of sets of propositions, and of arguments.